Today's lesson is on even and odd functions, and we're just going to go ahead and tie in the concept of even and odd degree so that students can see the comparison when using those terms. So just below the title, we have a box giving us the definition of even and odd functions. We are given the definition with respect to the graphical approach, and then we're given one with respect to the algebraic approach. Let's read. If the graph of a function f is symmetric with respect to the y-axis, we say that it is an even function. On the other hand, if the graph of a function is symmetric with with respect to the origin, we say that it is an odd function. That is, for every x in the domain of f, f of negative x is equal to negative f of x. And I realized that I did not read the part for the even, the algebraic part. So for every x in the domain of f, f of negative x is equal to f of x. So exactly what does all of this mean? Well, we're going to focus primarily first on the graphical approach. So again, when we're talking about even, there's going to be symmetry with respect to the y-axis. This has to do with even functions. And then with odd functions, there is symmetry with respect to the origin. We call that the odd function. So let's scroll down to the lower part here, and I want us to take a look at question number 1. Look at the graphs A, B, C, and D. When we are talking about symmetry with respect to the y-axis, what I want you guys to visualize is that when a graph is sitting on the graphing plane, if you are able to fold your paper, let's say, on the y-axis itself, what is going to happen if it is an even function is that the function itself will overlap with the other side. Okay? So if you look at these 4 graphs, which one of these 4 graphs, or which ones of these 4 graphs are even functions? Take a moment to make a note of which ones you think are even functions. If you chose graphs B and D to be the even functions, you are correct. Okay. Why? Because they are symmetrical about the y-axis. If we imagined ourselves folding the paper that your graphs are sitting on right now on that y-axis, this side right here would most definitely overlap with this side. Same goes with this problem. This side would overlap with this side. Now let's look at the odd function. The odd function, there's symmetry with respect to the origin. So between these two, or do both of these have symmetry with respect to the origin? Now the origin is the 0, 0, the center here. Well, we're going to notice that only graph A has symmetry about the origin. Okay? Now, the reason I'm writing SYM next to these words is because eventually we're going to compare even and odd functions and even odd degree. So I wanted you to know that right now we're speaking about even and odd functions with regards to their symmetry. Graph C does not have either odd or even symmetry. Okay? And that has to do with symmetry as well. Now, what does symmetry about the origin look like? So here's what I want us to realize. Symmetry about the origin is basically going to have a reflection over the x-axis and then the y-axis. Okay, now it doesn't have to be in this order. You can reflect over the y, then the x-axis, but I want you to imagine this, okay? If you look at graph A, and let's just imagine taking this piece of the graph, okay, I'm going to put dashed lines, and I want to reflect it over the y-axis, okay? Let's say I wanted to reflect it. Would you not agree that that graph would then end up kind of imprinting itself on this side, like so, okay? That's the reflection over the y-axis. But then let's say I take that new imprinted line and reflect it one more time over the x-axis. Do you not see how this highlighted dashed blue line will now become this darkened blue line right here that overlaps the piece that we ignored, okay? So can you see how that rotation is occurring about the origin? 0, 0, okay? That's the odd symmetry perspective that I'm talking about, okay? So in our table, or not our table, in the rectangle above, we have addressed symmetry with respect to the y-axis and the origin. Now let's talk about the even and odd degree. What does even and odd degree mean? If you would, take a moment and go ahead and copy down this definition. Okay. So end behavior of graphs determine whether or not the function has an even or an odd degree. So now notice, I'm not asking you to determine if the function is an even or an odd function. I'm asking you to determine if the function has an even or an odd degree. Even or an odd degree. Okay, something completely different. So all our graphs, our continuous function graphs, are going to have ends, okay? The ends are either going to be pointing both up or both pointing both down, or the ends are going to point in opposite directions, as you see in the pictures below. Even ends point in the same direction. Odd end behaviors, arrows point in the opposite direction. So what I would like you to do is return to the 4 graphs that we were working with. I would like you to go ahead now and determine what kind of end behavior do these graphs exhibit. Do they have an odd degree or an even degree function? Go ahead and pause the video and take a moment to do that. Okay, you're back. So A and C are identical in the sense of what their arrows are doing. So even though the graphs don't have arrows drawn on them, feel free to go ahead and draw these in. These are implied. So A has an odd degree function because the arrows point in opposite directions. One's going up, one's going down. Whereas graphs B and D, they both have even degrees because the arrows are pointing in the same direction at the same time. Okay. Just so you know, we'll spend a lot more time on this in the future, but the degree of a function merely is what is the highest exponent, the power of your function. So when your function is written out, so for instance, in problem number 2, part A, f of x equals 3x to the 4th minus 5x squared plus 17. If you were asked to determine what the degree of that function is, the degree is the 4. 4 is your highest exponent. Okay? So just wanted to make sure you understood where the word degree is coming from. So anyhow, you can determine if a function has an odd or an even degree exponent value, that highest exponent value, just by looking at the behavior of the ends. So now let's look at the next feature with regards to even and odd functions, but this time in the context of the algebraic approach. So this definition here and this definition here. So I'm going to try and help you understand a little bit more clearly what those two equations are exactly trying to explain or help you understand to determine whether a graph is even or odd. F of negative x equals f of x is the even function definition, and f of negative x equals negative f of x is the odd function definition. So what does that function notation equation signify? So what I'm going to do is give you some sort of visual to help you understand what is boxed in those equations. So let's look at this first image right here. Okay, so the first equation for even was this, and here's the visual that I'm trying to get you guys to understand. So let us pretend that you have to choose two numbers to put into this function box. Now what I need you to understand and recognize is that both of these numbers, one has to be a positive and one has to be a negative. That's what x stands for. The variable represents a number. Both numbers have to be positive or negative. And notice, since this says x or negative x, they want us to choose the same number, okay, just opposite in signs. So for instance, you can randomly choose a 3 and a negative 3, or a 7 and a negative 7, and so forth, okay? You are going to put in, ergo the word input, the two randomly chosen numbers, okay? These numbers are random, so let's make sure we remind ourselves. Randomly chosen. All right. You are going to choose these two randomly chosen numbers and you are going to put them into the function box. Now, I do not know what the function is. The function can be x squared plus 5. The function can be negative 9x cubed minus 7x plus 10. You know, I don't know what the function is, but whatever the function is, you are going to substitute those values into the function. You are going to substitute it for every x. Once all the simplifying of that function happens, okay, it's going to spit out, for lack of better words, two answers, because you are going to put the first value you chose into the function, let it do all its work in here, and it's going to result in an output value. And then you're going to substitute the next number you chose into the machine, the function. All the simplifying is going to happen, and then another answer is going to be coming out, right? So what you're telling me is that if you randomly choose an x and then you do all the work that needs to happen, you're going to get an answer spit out, okay? And if I substitute negative x into the function and I do all the work, I'm going to get another answer, okay? That's how coordinates come about, okay? X and Y, X and Y. The thing that I need you to realize is that in this even case scenario, my Y coordinates are going to be the same. My Y coordinates, my answers, are going to be the same answer. That's what I mean by this expression, okay? That f of negative x is the same as f of x. So for instance, if they were both the same, let's erase these coordinates here, and we're going to pretend that x and negative x was a 3 or a negative 3. We substitute the 3 into the function, and once we simplify, the 3 yielded a 10 as an answer. Then we put in the negative 3 into the function. We did all the simplifying, and then it also ended up in an answer of a 10. So what you're telling me is that when 3 is substituted, you got a 10. That's one coordinate. And then when negative 3 was substituted, you also got a 10. When this occurs, when you realize that your x values are the same, you have determined it to be an even function. Okay? That's what this boxed f of negative x equals f of x means. Okay? Because here's what I want you to realize. 3, 10 is the same thing as saying, if I take a 3 and I put it into my function machine, I'm going to get a 10. And if I take a negative 3 and I put it into my function, I'm also going to get a 10. Well, if f of 3 is 10 and f of negative 3 is 10, isn't it safe to say that f of 3 is equal to f of negative 3? And since even functions values will all behave the same, we can assume that any x that's chosen will always equal the opposite value of x being substituted into the function, end up having the same value. So that's the definition of even. So the same approach can be taken with odd. Okay, so let's look at what odd does. Okay, here we go. With odd functions, we look at the top of your page and see how they wrote that equation in that rectangle. So f of negative x is equal to negative times f of x. Okay, so here's the difference. You're still choosing a random x or a negative x to be put into the function. And when you finish doing all the simplifying of that function, all the order of operations and combining of like terms, when you end up with an answer, the answers are going to be the same, but with one little adjustment. Both answers must be opposite in sign. Okay, so using a similar approach that we did upstairs, pretending that we are substituting a 3 or a negative 3. If you substituted the 3 into the function and you did all the math, you ended up with a, let's say, 8. And then you took the negative 3, substituted into the machine, and after simplifying, you will end up with a negative 8. So the numbers were not the same, but they were almost. The only difference is they were opposite in sign. When that happens, you have proven or verified that your function is an odd function. Think of O for opposite. So here's what I want you to do. I want you to come over here to your problems, and the ones that are highlighted, A, C, B, and D, I want you to randomly choose an x value to substitute, or two x values, because one has to be positive and one has to be negative. Choose a randomly chosen value and substitute it into your equation and simplify. And tell me what numbers are generated, what are your output values, and once you compare them, you are able to determine if it's even, odd, or neither. So go ahead and pause this video. Again, remember, it doesn't matter what x value you choose, because regardless of the x value you choose, the same result will come out as far as the pattern, not the value, the pattern. Okay, so hopefully you have all your work ready to go. So let's look at part A. F of x equals 3x4 3x to the fourth power, my bad, minus 5x squared plus 17. So I'm going to use Desmos to kind of help us along to see what's going on. Now, here's the equation I just read out to you, and graphically we can look at this and we can easily see right off the bat, and I lost it. Hold on here. We can easily see right off the bat that if we folded this graph over the y-axis, that this side right here would definitely overlap with this side over here. Okay, so my question now is, were you able to do this though without looking at a graph? So if you chose any random x value, all right, you would have ended up with the following. So, oops, I'm opening up the wrong things. Let me bring this back. Where is it? Okay. This is not turning out as I wanted it. Okay, so if you click on this little wheel right here, by the way, if you weren't unaware of this, you can create a table. And I don't know what x values you ended up choosing, but here's the pattern that I'm noticing. If I substituted -2 in this equation, my answer ended up with a 45. If I substituted +2 in this equation, I ended up with a 45. -1 with a 15, 1 with the 15. So as long as you chose an x value and evaluated both the x positive and the x negative, notice that the values always ended up being the same, right? I don't know what x you chose, but just to prove a point, you can just continue generating more values, okay? So what I'm saying is, coming back to this right over here, so -2 and +2x gave us output values of 45. So I can easily say, since f of 2 gave me a 45 and f of -2 gave me a 45, I know that by definition, and I don't have enough space to write this down, so I'm going to write over here that whoops, let's scoot over here a second, that f of x was the same as f of -x. And because they are the same, I can categorize this as an even function. Okay? That's what you do to be able to prove that. So let's look at another one, right? Let's go back to this one. Let's turn this one off right here. And let's look at this one. So let's see. Let's make this one a little bit smaller. Here we go. So I'm going to turn off this table. So this table right here, or this graph right here, just graphically looking at it, I can tell it's going to be an odd function, right? I can take this piece of this graph and flip it over the x and the y axis and rotate it, and it will end up overlapping this one. So this is going to be an odd function, and just in case we are unsure, let's create a table for this blue function, and let's look at those values. So at +2 and -2, the numbers, there you go, 1580 and 1580, but opposite in sign. And once you have identical numbers but opposite in sign, that is an odd function characteristic. -1 and 1 gave me a -16 and a +16. So I can come and let's use the 1 and -1 on this one. Okay, so I'm going to write, let's see if I write smaller, that would be better. If f of 1 was equal to, oh my goodness, what was it again? -16? Yeah. If f of 1 equals -16 and f of -1 equals to 16. Let me make sure I did choose the right one again. Let's see. F of -1 is negative and the other one's positive. Whoops. And f of -1 is negative and f of 1 is the positive, right? We notice that the numbers are identical but opposite in sign. So I have proven that my f of x times a negative is going to be the same as f of -x. Okay, so that is an odd function. So we just continue doing that and choosing random numbers, and you are able to prove whether it's even or odd. So in problems D and F, you should have chosen them to be neither and odd. If you want to look at it just from the graphical perspective, here we go. The neither x cubed minus 7. This one was a neither one. It neither reflects over the y-axis to overlap, and if you rotated it, it would not work out. It would not be symmetrical about the origin. And then over here, let's look at this other one. This one was the odd. You definitely could reflect this over the x-axis, so it'll end up looking like that. And then you could flip it over you would reflect this over the x-axis, and then once it's imprinted on this side in quadrant 1, when you reflected it over to this quadrant, it would definitely overlap with this. So this is an odd function. Okay, so last part of our notes. There are other parts that you can fill out. The answer keys are on Canvas, but this was the last piece that I wanted you guys to work on. So table A shows a even function set up for a graph, and the other table is an odd function. I would like you to take the time and fill out the table with the missing values now that you know the characteristics of each. So pause the video now and we'll get going with the answers. Okay, let's fill this table out. So even function says the y values are going to be the same. F of x and f of negative x are going to be identical. So what we do is we need an x and a negative x. All right. So let's figure out what x and negative x we have. So if we focus on negative 5, we need to focus on 5. Negative 5 and 5 must be equal to each other as far as their output values. Remember, negative 5 and 5 are going into the machine, and the answers that come out of the machine have to be the same. They have even means the same. If you're even, you call it even with somebody else, you're on the same level. You're the same. So if negative 5 had an output value of an 8, that means 5 also has to have an output value of 8. We keep on with that repetition. Well, negative 4 is going to give us an output value of 6. So the opposite of negative 4 is 4. 4 also has to generate a value of 6 if it's an even function. Now, they didn't give us negative 3 and negative 2, but they gave us positive 2 and positive 3 down here. Well, 2 gave us a 0 and 3 gave us a 4. So, if 2 gave us a 0, then negative 2 also has to give us a 0. If 3 gave us a 4, then negative 3 also has to give us a 4. Okay? 1 is paired up with negative 1, so it has to be identical as what negative 1 output value is. And this here would be 0, 0. If you can visualize it, has a parabolic effect. Okay? Odd, a little bit different. Odd says, hey, when you look at the positive and negative x, the output values that you get, output are the y values. The output values have to be opposite in sign. The number is the same, but opposite in sign. So if negative 5 is giving us a negative 6, that means positive 5 is going to give me a positive 6. If 4 is giving me a negative 3, my 4 is paired up with negative 4. That means negative 3 with the negative 4 is going to be positive 3. So I have to choose the opposite. Okay, O for odd is opposite. So I want you to notice here, and let me show you here as I pair it up. Look at this negative 6. The opposite is positive 6. 3, the opposite is negative 3. The output values here have to be opposite. Okay, OPP. Over here, my output value 8 is paired up with this 8. That has to be the same. The x value is negative 5 and 5. Let's look at negative 2 and 2. Negative 2 and 2. Those are the same. Let's look at negative 4 and 4. Those are the same. Even have to have the same y values. Okay? So I'm hoping you see that pattern developing. So 5, this has to be negative 5. 1 is 3, so negative 1 has to be negative 3. This will be my 0, 0. And 3, so negative 3 had a negative 2, so 3 has to have a positive 2. So there you go. That is the answer, and that is our lesson. Thank you so much for watching.